Okay, so now that what's happening when you are doing a double integral, something like this, f of x, y, dx, dy on some domain D. Okay, let's see. If your domain D, let's suppose that your domain D is very simple to write. It's just a rectangle, AB, interval AB times interval CD. So that if I read that correctly, that should be X is in AB and Y is in CD. So let's take, for instance, look at this graph on the side here. Let's say that's the representation of some function f of xy, and I'm interested in x is between, let's say that is x, and we'll say that x is between 5 and 10, and y is going to be between, well, that looks like negative 40 up to negative 30, okay? So that the intersection, that's the rectangle I'm talking about. AB times CD is going to be that rectangle. Okay, if you're looking at the plot that is given, it looks like this rectangle is plotted as this part of the surface. Okay, and when we are doing this integration, we are calculating the volume of this thing here. So the volume below the surface, between the surface and the area of the plane that is described by our domain. Okay, and how does that work? So it's a volume. For a positive function, it's going to represent a volume, and again, if your function takes negative value, you would take a signed calculation of the volume. Right, so how does that work? It works exactly the same as before. You're going to approximate this thing by taking volumes that you can easily compute. Okay, so namely cuboids. Okay, so that's going to be constant value. So that's an easily computable volume. So that's dx, that's dy. That would be f of some value inside of this rectangle, and that's it. And this, you know very easily how to compute that volume. You're making f of x0 y0 times dx times dy. Okay, see where I'm coming at? So I didn't use the delta, but the idea is that that would be some delta, and as if you want to compute the whole volume below a surface on some big areas, you would just sum over all different values of x0, y0, let's say xk, yk. That would define points in all your small rectangles, and then in the end that tends to be called, when the widths dx and dy become infinitesimally small, become infinitesimal values, then that's going to, your sum is getting to something continuous that really is the real value of the volume. Okay, this was approximation, the sum was approximation of the volume. Now when your dx dy become as small as possible, the limit of this value is going to be the volume, right? And that's what would be called the double integral of f on that area. Okay, all right, so now what's happening when you are doing some substitution? Okay, so now let's consider that infinitesimal rectangle, meaning that's going to be du and dv in the uv variables. Okay, so that means that if it's that's a rectangle of size du dv. All right, what we want to understand so is that how this is affected by function phi. Okay, that's going to give you something in the xy plane, and that should correspond to some, sorry, in the xy variable, and I didn't make it straight because, well, your substitution may not be a linear one, so it may not look exactly like a rectangle, but then it's going to be something that has an area that we would call dx dy. Okay, even though it may not look like a rectangle. So let's try to understand what's going on here. Okay, so we have, let's start with this du dv stuff. So we have something with coordinates. We begin with coordinates uv, right? And here we've got u plus du, v stays the same. On the other, that corner, we're going to have u and v plus dv, and on that corner we're going to get u plus du, v plus dv. Okay, and of course that has length du and that has length dv. Okay, so now if we apply phi to that stuff, let's take at least the images of our four corners. So that corner is going to have phi of uv. Okay, that corner is going to have phi of u plus du v as coordinates, and so on, phi of u plus du, v plus dv, phi of u, v plus dv. Okay, and what I want to know is to get an approximation of that area. Okay, knowing that the area of this area is dx dy. Oh, sorry about that. This area is du dv, and I want to know. Okay, and that's supposed to be dx dy, and we want to know the relation between those two areas. So let's try to get, let's say that this is going to be approximated by the area given by two vectors, this vector A and that vector B. Okay, they appear more or less straight with a right angle, but it's not supposed to be a right angle. It really depends. Okay, and that's just going to be an approximation because my function phi does not have to be linear, so that my straight line of length, my straight segment of length du won't be sent to a straight segment, but we're doing approximation. In the end, that works. That's the idea. If you write things rigorously with the right limits everywhere, things get neat, and it does work. But so, however, let's write what we have. So we want to find the coordinates of the vector A. The vector A is going to be given by phi of u plus du v minus phi of uv. Okay, so that's just x of u plus du v, y of u plus du v minus x of u v, y of uv. Okay, so these are two coordinates. So if I write them as a column vector, I get x of u plus du v minus x of uv, and second component of the vector a. So that's my vector a, y of u plus du v minus y of uv. Well, you know how to get approximation of that. That's just going to be the first terms of the Taylor expansion. So that's going to be the increase in the first variable u, so du times derivative of x with respect to u, so dx over du. Okay, and same thing for the bottom component. It's just going to be increase du times the partial derivative of y with respect to u. Okay, with a very similar reasoning, we get approximations of the vector b, and that's just going to be x u v plus dv minus x of uv, well, y of u v plus dv minus y of uv, and that's just going to be given by increase, so that's dv times dx over dv and dv v times dy over dv. Okay, so for this one. Now, if I want to get that approximation, the approximation of, sorry, of this area here, all right, indicated by vectors a and b, you know, it's just going to be the determinant of the matrix given by vector a and b written as column vectors. Okay, and we take the absolute value. Okay, that's properties, that's how you compute determinant, areas of parallelograms that are indicated by two vectors in R2, right? So let's compute that. So we have, let me even rewrite it as dx over du times du, dy over du times du, that's my vector A. My vector B is going to be similar, but in v, dv, dy over dv, dv. And what do I get if I do this computation? I get, so dx over du, dy over dv, dx over du times dy over dv, minus dx over dv times dy over du times du dv. And here we are. That's the relation that you have for the area that should be indicated by dx dy. That's given as du dv times this value. And this value, well, it happens to be also the determinant, absolute value of the determinant of the Jacobian matrix of phi. Okay? So this is why you get this relation when you want to substitute the infinitesimal term in your double integral. It's going to give you this substitution. You will have to write that dx dy is substituted by absolute value of the determinant of the Jacobian of phi times du dv. Furthermore, one nice thing is that if you've got, so this was when x, y were given as functions of u and v, okay, which is going to be sometimes the case. For instance, in the polar coordinates, this is how it is given. But if you have the contrary, if you have u, v as, well, if it is given as a function of xy, I'm writing it here as phi minus 1 because just to be consistent with my previous notations. But if it's given as phi of xy, you just know that, well, it happens that the Jacobian of phi minus 1 is really the inverse of the Jacobian of phi. Okay, and so the determinant of this one is really the determinant of this one minus 1, which we find again here. Okay, we have that 1 over the determinant of phi, of j phi, the Jacobian of phi, dx dy is equal to du dv, and this is really just as saying that we have here the determinant of phi, of the Jacobian of phi minus 1, dx dy equals to du dv.